All right, let's dive right into today's explainer. We're going to look closely at energy systems and their trade-offs. To do that, we really need to demystify some of those abstract concepts, like mechanical energy and heat, and ground them firmly in the real world. To hook you right away, we've got to bust a major physics myth. Imagine you're carrying a really heavy rock across your lawn at a perfectly constant speed. I mean, it feels exhausting, right? But scientifically speaking, that effort actually requires zero work. Zero. I know, it sounds totally crazy, but by the end of this explainer, you're going to understand exactly why. Here is our macro to micro roadmap for today. 1. Work, power, and energy. 2. Kinetic and potential energy. 3. Conservation of mechanical energy. 4. Understanding specific heat. And 5. Conduction, convection, and radiation. Okay, section 1, work, power, and energy. Let's start with the basics and redefine some everyday words that actually have very strict scientific meanings. So the absolutely crucial point here is that work only happens when a force actively moves an object over a distance, specifically in the direction that the force is applied. We measure this in joules. The equation is super simple. Work equals force times distance. Now notice the contrast here between everyday English and physics. Mental effort, like doing your homework, or simply holding a heavy object up without moving it, that's not scientific work. Why? Because there's no physical movement over a distance in the direction of the force. However, the act of actively lifting that rock upwards off the ground, now that is work, because you're applying an upward force and moving the rock upward against gravity. This whole concept of work brings us to an incredible historical figure, James Watt. He revolutionized the steam engine, taking early designs and converting their clunky back-and-forth motion into smooth circular motion. And really, this is the foundation of traditional energy systems, like coal-fired steam plants, where burning fuel transfers heat into mechanical work. When we look at system trade-offs, these steam plants offer incredibly high reliability. I mean, you can burn fuel to generate power at literally any time of day. But historically, they've had massive environmental impacts because of their emissions. Watt's innovation brilliantly illustrates our next concept, power. Measured in watts, named after the man himself, of course, power is just the rate at which work is completed. You simply divide the work done by the time it took to do it. All right, time for a quick pause check. If you run up a flight of stairs instead of walking, did you do more work? The answer is no. You moved the exact same mass of the exact same vertical distance, so the work done in joules is identical. But, and here's the kicker, you generated much more power because you completed that work in significantly less time. Let's jump into section 2, kinetic and potential energy. Let's see how doing this work actually changes an object's mechanical energy. Think of work as the currency we use to give an object energy. We can give it kinetic energy, which is the energy of actual motion, like a speeding car, or we can store that work as potential energy. A great example of this is lifting a roller coaster car up a massive hill. The higher it goes, the more gravitational potential energy it stores up, just waiting to be released. Moving right along to section 3, conservation of mechanical energy. Let's see what happens to that energy in a closed system. Imagine that roller coaster, or a skater dropping into a half pipe. At the very top of the hill, before the drop, you've got maximum stored potential energy. As you plummet downward, that stored energy violently transforms into kinetic energy, maxing out your speed at the absolute bottom of the drop. Then, as you coast up the next rise, that kinetic energy smoothly converts right back into potential energy, slowing you down as you climb. This reveals a literally perfect accounting system in physics, known as the law of conservation of energy. In a closed system, total energy is completely constant. It's never created, never destroyed. It is only perfectly transformed between these potential and kinetic states. The total mechanical energy you start with is exactly what you finish with. So here's our second pause check. If energy is never lost, why does a skateboarder coasting back and forth in a half-pipe eventually come to a dead stop without pushing? Well, the skater stops because real life isn't a perfectly closed system. Friction between the wheels and the ramp, along with air resistance, is constantly bleeding that large-scale mechanical energy out, converting it into microscopic kinetic energy, which we actually feel as heat. Which brings us perfectly to section 4, understanding specific heat. We're going to zoom all the way down to the micro level, looking at heat as just the chaotic, microscopic motion of atoms. Because temperature is really just a measurement of the average kinetic energy of these tiny particles, a concept called specific heat tells us how much energy is required to get those specific particles moving faster. It's strictly defined as the amount of heat needed to raise 1 kilogram of a material by 1 degree Celsius. Check out the data for water here. It has a massive specific heat of almost 4,200 joules. That is roughly 5 times the specific heat of aluminum or glass. It takes a tremendous amount of energy to change water's temperature. And this is exactly why our oceans act as giant climate stabilizers for the entire planet. It's also why major energy systems, like those power plants we talked about earlier, rely so heavily on water for cooling. Its incredible efficiency at absorbing excess thermal energy is basically unmatched.
And now our final section, number 5, conduction, convection, and radiation. Let's explore exactly how this thermal energy gets around.
Thermal energy generally moves in 3 ways. First is conduction, which relies on direct physical contact. Think of a hot pan on a stove. The fast-moving atoms in the hot burner literally collide with the atoms in the pan, transferring that kinetic energy. Next is convection. This relies on the physical movement of a fluid or a gas. When a fluid heats up, it expands, becomes less dense, and naturally rises because of buoyancy. You see this in a boiling pot of water or on a massive scale in our global weather systems. The final method is radiation, which is a bit of a rule breaker because it requires absolutely no physical medium or matter to travel through. It moves as electromagnetic waves. This is how the sun's energy travels through the total vacuum of space to warm the Earth. And this brings us to another major energy system option to compare: solar power. Now, solar panels offer incredible environmental impact benefits because they're clean and just capture this radiant transfer. But the trade-off is reliability. Unlike that coal plant that can burn fuel on demand, solar relies on the sun shining, making it intermittent, and the overall system efficiency fluctuates heavily depending on the weather. To really tie mechanical energy directly to thermal energy, let's look at a visceral physics example. A heavy 10,000 kilogram truck breaking down a steep 75-meter hill has to dump an immense amount of gravitational potential energy. Traditional brakes must literally absorb millions of joules of energy, transferring it entirely into terrifying, water-boiling heat, spiking the brake temperature by over 90 degrees Celsius. But in modern energy systems, like electric vehicles, regenerative braking actually captures that mechanical energy, transferring it back into the battery. This massively improves overall system efficiency instead of just wasting it all as heat. Let's bring it all together for a quick recap of today's explainer. Energy is the universal currency of movement. Work is using force over a distance to transfer that energy, and power is the speed of that transfer. We saw how energy smoothly transforms from large-scale motion, kinetic and potential, all the way down to the micro-level friction that generates heat. We also learned how specific heat makes water an amazing temperature stabilizer, and how heat ultimately moves via conduction, convection, or radiation. Let's test your understanding of conduction with a real-world transfer question. Imagine stepping out of bed in the morning. If the carpet and the bathroom tile floor are the exact same room temperature, why does the tile feel freezing cold when you step on it barefoot, but the carpet feels totally fine? Well, it's because the tile is a much better conductor of heat. It rapidly pulls the thermal energy out of your warm foot, creating that intense sensation of cold. I'm going to leave you with this final, provocative thought to ponder. If energy is never truly created or destroyed, but only perfectly transformed, where does all the heat energy from every vehicle that has ever braked or every skateboarder that has ever coasted to a stop eventually end up? Keep wondering about that, and thanks for exploring the amazing world of energy with me today.